In this video, we will explore how Type 1 and Type 2 errors work in the context of quality control through a case study. In quality control, the primary goal is to ensure that products meet certain standards before they reach the consumer. To achieve this, statistical tests are employed to decide whether a batch of products is acceptable or not. This process involves formulating the null and alternative hypothesis. A Type 1 error occurs when a quality control test rejects a batch of products as defective while in reality they meet the quality standards. This leads to an unnecessary waste and increased costs. A Type 2 error occurs when a quality control test fails to identify a defective batch of products, which can result in customer dissatisfaction, safety risks, and damage to the company's reputation. The optimal balance between these two errors depends on various factors, including the cost of discarding good products, the potential consequences of shipping defective products, and the overall quality goals of the company. Let's explore this balance with a case study where we'll calculate these errors and set practical limits. A ball bearing factory is implementing a new manufacturing process and needs to evaluate its impact on the quality of their bearings. The factory aims to produce bearings with a diameter of 10 millimeters. They are concerned about the potential for the new process to cause deviations from this target diameter. To ensure quality, the factory employs a hypothesis test on samples of 50 bearings from each batch. They want to determine the appropriate balance between two types of errors associated with their quality control test. They initially set the significance level at 1% and use a population standard deviation of 0.2 millimeters based on historical data. Now, in this case, a Type 1 error occurs when they reject a batch of bearings when the average diameter is actually 10 millimeters. Because they've chosen a significance level of 0.01, there is a 1% chance of making a Type 1 error. A Type 2 error occurs when they fail to reject a batch of bearings when the average diameter deviates from 10 millimeters. They calculated the probability of a Type 2 error when the true mean diameter is 10.1 millimeters. In this case, the probability of a Type 2 error is defined as the probability of getting a test statistic outside the rejection region when the true mean is 10.1 millimeters. In a sample distribution of the sample means, the region between Z alpha by 2 and Z1 minus alpha by 2 represents the acceptance region, that is, if the observed sample mean lies in this region, we fail to reject the null hypothesis. These threshold limits can be obtained from the Z-distribution table by locating the probability value of alpha by 2 that is 0.005 for the left tail limit and the probability value of 1 minus alpha by 2 that is 0.995 for the right tail limit. To define the acceptance region in terms of the sample mean, the Z-score formula was used to calculate the threshold limits, which are 9.927 millimeters and 10.073 millimeters. If the sample mean falls within this range, the null hypothesis will not be rejected. Now, with a sample size of 50 and assuming a true mean of 10.1 millimeters, they calculated the probability of a Type 2 error by determining the chance of the sample mean falling within this acceptance region. To do that, they first calculated the Z-score corresponding to this alternative true mean, taking into account the standard error based on the sample size and known population standard deviation. These Z-scores determine the probability of observing a sample mean within the acceptance region 9.927 to 10.073 millimeters, given that the true mean had shifted to 10.1 millimeters. This probability can be determined using a Z-distribution table by locating the corresponding Z-scores and finding the area under the curve between those values. This resulting probability represents the likelihood of a Type 2 error, which is the chance of failing to detect this specific shift in the mean diameter. This means if the true mean diameter of the ball bearing shifts to 10.1 millimeters, there's a 16.86% chance that their quality control test, with a sample size of 50, will fail to detect this deviation. This plot shows the potential errors in a hypothesis test used to determine if the mean diameter of ball bearings has shifted from the target of 10 mm. The red shaded areas show the type 1 error, which has a probability of 0.01. The blue shaded area represents the type 2 error, which has a probability of 0.1686. This plot helps the factory visualize the trade-off between type 1 errors and type 2 errors, allowing them to adjust their quality control process for an optimal balance. If you'd like to test your knowledge on this topic, be sure to check the quiz link in the description below or visit our community page. Thanks for watching. Please like and subscribe for more statistics content.